t over 2 to t. Okay, so let's just like see what happens here. This becomes vd over pi times negative of cosine. If I replace t with t over 2, becomes negative cosine pi plus cosine 0 plus cosine 2 pi minus cosine pi. Cosine of pi is negative 1, so this becomes positive 1. This is 1. Cosine of 2 pi is 1. Negative cosine of pi, this is negative 1 minus negative 1 becomes plus 1. So this becomes, let's see if I made any mistakes here. Negative cosine pi plus cosine of 0 plus cosine 2 pi minus cosine pi. That's correct. Actually, this was vd over 2 pi. That's the mistake I had. Sorry. So then this becomes 2 vd over pi. Okay, so the whole calculation was to find the coefficient for v1. Okay, so this basically tells us that this signal can be written as 2 vd over pi sine of 2 pi over t plus summation of other bn's sine of 2 pi over t times nt, where n changes from 2 to infinity. Right, the DC component was 0. All the cosines are 0. Right, so these are the harmonics that we don't need. They're undesired. Okay, so this is the fundamental signal, and this is the peak value of the fundamental signal. So our B1, which is here, this basically tells us the coefficient for the peak value of the fundamental frequency, right? Which is definitely smaller than this one, right? But this is the peak value. So if I want to find the RMS, V sub 1 RMS, I have to divide this by root 2. So it becomes root 2 times Vd divided by pi. Okay, so this is what we have so far. Now, let's see what's the total RMS value of this signal. So what I'm gonna do is finding the total RMS value of the signal. This was the RMS value of the fundamental frequency it's inside the signal. Now I want to find the RMS value of the whole signal. And I'm just going to use the definition 1 over t integral of 0 to t vt squared dt. Okay, this is, if I like raise this to power 2, it's the same as this one. So it's very easy to calculate this one. It's going to be 1 over t integral of 0 to t vd over 2 squared dt. Okay. Yeah. So then, because it's constant, it's easy to calculate its RMS value. It's going to be it's the integral, sorry. So it becomes basically VD over VD squared over 4 times T, where T changes from 0 to T over, or sorry, to T, the limits of the integral. Right, so that's what we have. The integral of a constant is that constant multiplied by t. So let's see what the value is. It's gonna be root 1 over t times vd squared divided by 4 multiplied by t. These cancel out. It would be vd over 2. Let's see if I make any mistakes here. No, seems okay. So we found the RMS value of the total signal, which is VD over 2. It was like obvious, like we didn't have to do it because the RMS value of this signal is the same as the RMS value of this signal, and it's gonna be VD over 2. Okay, so now this RMS value is equal to the RMS value of V sub 1 RMS value raised to power 2 plus V of all the harmonics raised to power 2. So this signal is made of the fundamental frequency plus many different terms. We just called all of those terms VH raised to power 2. Okay, I have this one, I have this one, I want to find VH. So I can write down VH, which is the harmonic, the RMS value of the harmonics, is root of V RMS squared minus V1 RMS squared. These are like vectors. If you want to add two vectors, the magnitude of them, this is like how it's done, right? So exactly like that. So like basically this is what I'm saying. This is like V1, this is V harmonic, and this is the total RMS value, right? So this is what we have. Now let's just like replace the values that we have here. V of RMS is gonna become VD squared over 4 minus 2 VD squared over pi squared. So V harmonic is going to be equal to VD comes out, and I can take